Thank you, Ken. I'm really pleased to be invited to this. This is pretty cool. I didn't realize this was such an event. You got so many people to come to these things. What's especially cool for me as a guitarist is that Skunk Baxter is coming next time to give a talk. He was one of my early inspirations. My talk is going to have a little bit of science and a lot of opinion. That's partly because even in science, while we sometimes can agree on the facts, we usually can't agree on what the facts mean. I get people that ask me, you deal with science, with things that you can prove to be true and false, and it just ain't that simple, especially in the area of global warming, where we've got a one-of-a-kind event that's supposedly happening now. We really don't have any way of testing it or falsifying it as a scientific theory, and there's a wide range of opinions. I'll tell you right up front that I would be considered to be part of the minority. And again, like I said, I'm going to be giving you probably more opinions than facts. But tell you what, we'll start out with the facts. The things that everybody can agree on. How about that? First of all, I like the details in my area of science. I also like to have a big picture view of how things work. I don't like to lose the forest for the trees. So what makes the atmosphere work? Well, obviously, sunlight is the source of energy, right? We all know that. Weather, what we call weather, is the atmospheric response. So everything you see with weather, all weather represents movement of excess heat from one location to another, both vertically from the surface, where most of the energy comes in and is absorbed, that's sunlight at the surface. You've got all this excess energy building up, and it either gets moved vertically, well, it gets both. It gets moved vertically and also poleward, because the tropics get a lot more sunlight than the high latitudes. So my major point here is that the atmosphere is always acting to get rid of excess heat. That's what makes weather work. That's what makes the climate system work. And we don't understand all the ways in which the atmosphere does that. This is just a simple cartoon. We'll just go through here quickly. Uneven heating of the Earth's surface, whether it's land or ocean, leads to circulation systems. I mean, you know about air pressure. Well, when you get uneven heating of air, it sets up pressure gradients in the atmosphere, and if there's a difference in pressure, the winds start to flow, and once the winds start to flow, some of them start ascending. If clouds start to form and release heat in the clouds. So anyway, you end up getting circulation systems that continuously cover the planet. And whether you're having a sunny day or a rainy day doesn't mean that the atmosphere is behaving any differently. It just means that you're either in this part of a circulation system or in the descending clear part of a circulation system. Now, the key thing to remember about climate is that of all the energy that comes in, the sunlight that comes in, there has to be an equal amount of energy going back out to outer space in order for the temperature of the Earth to remain constant. It's called energy balance. And that energy that goes back out to space is in the form of infrared radiation. Now, of course, we're more used to thinking of sunlight because we can see that, right? Our eyes see visible light, but not infrared light. But I think most of you have a feeling for what infrared radiation is. It's what you feel coming off of a fire. And in fact, after a sunny day, go outside and put your hand, after the sun is set, put your hand out over the ground, if it's still clear, or over, better yet, a driveway that's heated up, and go like this. and you can feel the bottom of your hand, the bottom side, getting warmed up. That's the difference in infrared radiation between the large amount of infrared radiation coming up from the ground versus what's coming down from the sky, which is very little. So you can actually use your hand as like an infrared radiometer. So anyway, the climate system involving weather systems evaporates water vapor from the earth, which removes a huge amount of heat carried up in rain systems, and there that heat is released. And the actual warming from all that heat release actually gets realized in the sinking air, where you think nothing is going on weather-wise on a sunny day, but actually that clear air on that sunny day is a very important part of the climate system. It is sinking in response to rainfall occurring in cloud systems far away from you. And it's all coupled together. And this is going on continuously all over the earth. It never stops. So that I talked about the movement of heat from the surface upward. But also there's this issue that the tropics receives a lot more sunlight than the poles. And in fact, if there wasn't export of heat out of the tropics towards the pole, the tropics would be unbearably hot and the pole would be unbearably cold. Well, I know it's already unbearably cold, but it'd be even worse. I've got this little animation that you saw when you came in. This thing here. We put this together a few years ago, and the reason I'm showing it here is because I never get to show it. We've never really had a use for it. Let me zoom this thing out a little bit. This is made from 2 different NOAA weather satellites, and this is microwave imagery of the temperature of air masses. It's averaged from the surface up to probably 8 kilometers altitude. We stitched all of this data together from these 2 polar orbiting spacecraft for, I don't know, maybe a 10-day period to see what the Earth looked like. And it's really a different way of looking at the Earth. You get to see, again, this is just a temperature field. You get to see the daily pulsing of the sunlight warming up the atmosphere over land, which you don't see over the ocean because the ocean has such a huge heat content. It has almost no warming during the day. And then you see these low pressure areas that help transport heat up to high latitudes, and for all the air that flows towards the pole, there has to be an equal amount of air coming southward, so you have these intrusions of cold air down south. This was a piece, I don't know whether you saw it, it kind of dripped off and sort of spun around there next to Hawaii. This is where you don't want to be in the wintertime, Siberia. Weather doesn't change a whole lot from day to day there. That's, I think, where global warming has been the strongest in the last 100 years, that now they have to deal with like 36 below rather than 41 below. I'm not sure, some average like that. But I think this is kind of cool, kind of dramatic depiction of the movement of heat around the Earth. Now, where does the greenhouse effect play into all this? Well, you might already know that when scientists talk about the greenhouse effect, we're talking about the Earth's natural greenhouse effect that keeps things habitable on the Earth for us. The main greenhouse gas is water vapor. Probably 90-95% of the natural greenhouse effect is due to water vapor. The bulk of the rest of it is carbon dioxide, and to a lesser extent methane. And these are gases that absorb and emit infrared radiation. They act as a blanket, and you really can use a blanket as an analogy. You know, if you're out camping or something and you only have a thin blanket over you, you don't stay as warm, and the outside of the blanket isn't that cold. But if you make that blanket thicker and thicker, the inside, where your body is, gets warmer and warmer, the outside of the blanket gets colder and colder. That's the way greenhouse gases work in the atmosphere. Is a greenhouse gas causes an atmosphere to be warmer below and cooler aloft than it would otherwise be without that greenhouse gas. And like I said before, this helps make the Earth habitable. This is just a cartoon showing that while the sun is a single source of solar radiation, of the sunlight, infrared radiation comes from everything. That's why it's hard to intuit what the effect of adding greenhouse gas to the atmosphere will do. You really can't figure out through intuition of what it'll do. You have to put the relevant equations into a model and run the model, except that we know that it will inevitably cool the upper layers of the atmosphere and warm the lower layers. But as you can see here, I just tried to point out with all these arrows that everything is a source for infrared radiation. The air, well, especially the greenhouse gases in the air, clouds, and the ground. What do we know for sure? Well, this is something we all can agree on. The carbon dioxide content of the atmosphere has been increasing. This is due to burning of fossil fuels that no doubt dominates it, especially since this increase, if you figure out how much carbon dioxide this is being emitted to cause this increase, we actually produce twice that much. Half of what we emit in fossil fuel use, carbon dioxide, gets sucked up by the biosphere since it's a food. Carbon dioxide is food, and some plant physiologists think that that the biosphere is starved for carbon dioxide, but that's sort of a philosophical point. That's what I just said. What about the official global warming estimates? Carbon dioxide is supposed to double in its concentration in the atmosphere sometime later in this century, probably. And the official global warming estimates are from the United Nations Intergovernmental Panel on Climate Change, the IPCC. This IPCC effort involves over 2,000 scientists, bureaucrats, and governmental representatives. The minority of this group is scientists. Very few scientists that actually are involved and know what's going on in terms of what climate models do. That represents a very small portion of that 2,000 people. They produce a new report every several years, and right now they've just started working on the next report. The main body of the report is pretty thick. It's got a lot of science details. It really is a good summary of what we understand about the climate system. Unfortunately, nobody ever reads the body of the report. The only thing that ever gets any press is the executive summary of this report, which is inevitably biased towards global warming is serious and even towards more philosophical points of view that countries of the world need to become less industrialized, less wealth generation, things like this that really shouldn't be part of a scientific report because that's sort of out of the realm of science, and yet they become part of and sort of the philosophical underpinnings of the conclusions that are in this executive summary. Now, typically in the news, you'll hear that over 2,000 scientists have agreed that global warming is serious, blah, 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 blah. Well, yes, there are 2,000 people involved in the process. There is an executive summary. Those people were never asked to pass judgment on this report. This report was generated, the words in this report was generated by a few select individuals. The latest I've heard in terms of what the current IPCC feeling is about how much our future warming is going to be up to the end of this century, starting from a starting point of 1990, is something like a range of 2.5 to 10.4 degrees Fahrenheit is something like what they're going to come out with in terms of a prediction. 2.5 degrees Fahrenheit would probably be livable. I would think 10 degrees is going to have some serious consequences if that were to happen. These estimates are based on climate models that are run on supercomputers. They're computer programs with the relevant equations that describe the radiation transfer in the atmosphere, the dynamics, the interaction of the atmosphere and radiation with the surface. Water is an extremely important part of these models because of all the ways that water interact with the climate system in terms of evaporation and rainfall and clouds especially. But the climate models are necessarily crude because, as hard as it may be to believe, computers are nowhere near fast enough yet to run the kinds of models we could put together and run with the understanding we have about the atmosphere. But since these things have to run globally, the model has to represent the whole Earth. It's a huge area, and you just can't make the model sophisticated enough. So they have to so-called parameterize a lot of processes, not the least of which is the effect of clouds. Now, I want to put this estimate into a context. It was back in the early 60s or mid-60s that scientists first published what the warming of the atmosphere would be due to a doubling of carbon dioxide just by itself. If nothing else happened, the atmosphere didn't do anything to respond, that the clouds didn't increase, didn't decrease. Evaporation didn't increase, didn't change. All you had was the extra radiative warming due to carbon dioxide. We reran that simulation recently, myself and a computational physicist that works with me. And what we got for a doubling of carbon dioxide alone was only 0.7 of a degree Fahrenheit. So you see that's even well below that. So all of this extra warming that you see in the climate models is because climate models tend to respond in such a way to amplify the warming. Now, depending on the climate model, they do that in many different ways. One model will decrease the amount of low clouds, and because clouds on average reflect sunlight and are a cooling effect on the climate system, then those models that reduce the amount of low cloud will have warming. And these are called feedbacks. This is what everyone argues about. People don't argue about this, the radiative effect of a doubling of carbon dioxide by itself. We understand the theory pretty well. In fact, we've flown instruments in space that can actually show us at the areas in the spectrum of light where we think the carbon, or where we know the carbon dioxide absorption lines are, we can actually measure how opaque the atmosphere is. We can see that blanket effect. So these are things that are measured and known. Now, the theory could be off by 10%, maybe, I suppose, 5 or 10%. But the big deal is, what do the feedbacks do? The feedbacks are the atmosphere's response to that initial warming tendency. We took this simple model run that only gave us 0.7 of a degree Fahrenheit warming, and if we assumed that the water vapor in the lower part of the atmosphere increased in order to keep constant relative humidity, which is a good baseline assumption, the warming increases to 1.4 degrees. And if we keep constant relative humidity throughout the troposphere, that allows the water vapor content to increase everywhere, which is probably too much on the warming side. We get 2.9 degrees warming. So you can see there's a wide range of possibilities for global warming. So everyone agrees that the warming tendency caused by the increasing amount of carbon dioxide in the atmosphere is going to cause some changes. But the atmosphere is always changing anyway. So the question is, how big are these changes compared to what the atmosphere does normally? There's probably going to be changes in clouds and rainfall. The question is it going to be big enough to measure? Can we predict it? Everything is going to change. I mean, the atmosphere, the Earth atmosphere system is a complex, nonlinear, interactive system with all kinds of feedbacks and interrelationships, and its climate models representation of these processes is still pretty crude. I already mentioned that the direct warming to carbon dioxide is pretty small. Positive feedbacks amplify the warming. Now, remember I told you that water vapor is the primary greenhouse gas, and it keeps the Earth habitable at a habitable temperature. Well, now I'm going to confuse you. Water vapor not only keeps the Earth warm, it also keeps it cool. Because water vapor, all water vapor represents the evaporation of water from the surface of the Earth. And when water evaporates, as you know, when it's on your skin and it evaporates, it removes a huge amount of heat. And in fact, about 75% of the potential greenhouse effect warming at the surface is never realized, because 75% of that heat gets sucked up by water, changes the phase to water vapor. The water vapor goes off and eventually gets rained out in precipitation. I've got this little animation here that I'll show. This is from an instrument on the NASA Aqua spacecraft. I'm sorry for the blinking. Try to ignore the blinking. We had to switch laptops. The projector wouldn't take my laptop. But anyway, these are daily total water vapor amounts over the ocean from this instrument that I'm the principal investigator on the NASA Aqua spacecraft. And what we see is that there's huge differences in water vapor. Of course, the biggest amounts of water vapor are in the tropics. And again, this is that greenhouse gas. Now you would think, wow, where there's a lot of that greenhouse gas, it must be really warm, huh? Well, no, there's really no temperature difference at the surface, or even in the up higher in the troposphere between there and there. It's because that water vapor has a much bigger effect in terms of its evaporation than its infrared effect. Once you get in the deep tropics, the atmosphere is pretty much opaque to infrared radiation anyway, because there's so much water vapor in it. Okay, now this is my main problem I have with present global warming theory. Most of the warming that climate models predict is directly or indirectly the result of this increase in water vapor that's expected to occur as a response to the warming from this warming tendency due to the extra CO2. And I've even talked to scientists about this, and it seems like everyone only emphasizes the fact that, well, if there's a warming tendency, it's going to evaporate more water vapor. Water vapor is the big greenhouse gas, so it's got to amplify the warming. Well, the amount of water vapor in the atmosphere isn't just the result of how fast water evaporates from the surface. It's a balance. The amount of water vapor that is in the atmosphere on an average is a balance between the source, which is evaporation, and the sink, which is precipitation. And there have been a number of papers in recent years pointing out that we really don't understand the microphysics of rain clouds and how they act to reduce the amount of water vapor in the atmosphere. We know that they do. There's water vapor is being evaporated almost constantly from nearly everywhere on Earth, because precipitation area is really the only place where that evaporation is shut off. So you've got all this water vapor that's constantly being evaporated everywhere, that's trying to pump up the water vapor content of the atmosphere, and these precipitation systems scattered here and there that take it as fuel and suck it up and dump it out as rainfall. That's the hydrologic cycle. It's part of the process that cools the planet. And we really don't understand. We do think we know, just based on anecdotal evidence, that rain systems in the tropics are more efficient. They're much more efficient at removing water vapor than high latitudes. And I know that, for me personally, some of the heaviest rains I've seen ever have come out of fairly shallow clouds over the Gulf of Mexico. Just amazingly intense rain rates. That indicates a rain cloud that is very efficient. It's not producing a whole lot of cloud, it's converting a lot of water vapor to rainfall. And a number of scientists are gradually admitting or realizing through their simulations that we really don't understand the processes that lead to precipitation efficiency, or that cause or that impact precipitation efficiency. That is, how efficient these systems are at removing water vapor. And this effect isn't included in climate models. So for instance, one scientist, well-known scientist that published these results, concluded that until we solve this problem, we can't quantitatively predict how much global warming there's going to be. Now, clouds is usually what you hear more about in terms of uncertainties. This is where all of the modelers that even believe in a lot of global warming agree that we really don't understand how clouds will change with global warming. They're very nonlinear processes that interact in complex ways. They're not explicitly contained in the models. I got interested in this issue a few years ago and got the latest state-of-the-art cloud resolving model. This is a high-resolution model that takes a lot of computer power to run, and we ran it. It'll grow thunderstorms, it'll grow tornadoes if you put in the right, you can grow anything. You can go down to the smallest scales and model the flow of air through this building or something if you want to. It's got those kinds of physics. And my intent was double the CO2 content of this model and see what happens. Because I was really curious, if you've got something that actually resolves the clouds. Well, I did that, and there was only maybe 1 degree of warming with doubled CO2, and I let it keep running. And then all of a sudden it warmed up to 2 degrees and stayed that way for another 6 months of model run time. And I thought, okay, so it's leveled off. And then it warmed up again, like to 4 degrees. This is degrees C, so now we're talking like 8 degrees Fahrenheit. And every time it was because the water vapor in the domain was increasing dramatically, and it was the greenhouse effect of the water vapor that was warming up the model, and it just kept on going up. I mean, it was a runaway greenhouse effect. So I started digging into the physics of these rain clouds. I mean, the physics in this model is so much beyond the parameterizations that is in these global climate models. And what I realized that for all of that code, the representation of clouds and precipitation processes was really crude. And I really began to realize that even for these models that are supposedly state-of-the-art, there's all these approximations and constants, variables that they put in a constant value of, and they say, well, we think it's something like this, and we have no idea how it changes with warming. I'm just trying to point out that it is my personal belief that the atmosphere is so much more complex than we think it is. This is some work I did several years ago with some Department of Defense weather satellite data. Was the only instruments we had back then that could measure the humidity of the upper atmosphere. This is actually fairly hard to measure, and of course we don't have any measurements over the ocean. And what we found was that these huge, I call them oceanic deserts, where there's really dry air. This is from the sinking air. I remember I was telling you about the clear air that's sinking. This air is sinking, slowly sinking and drying out, and it's being fed mostly by all these little thunderstorms that are occurring. So just think that these little thunderstorms, with all that water vapor going up and producing huge amounts of rainfall, all that air that's rushing up at 40 miles an hour is out here, gradually sinking all over the tropics at 0.001 mile per hour or something, some really slow sinking rate. Anyway, this is where a lot of that infrared radiation is lost. The drier this air becomes, the more efficiently it emits radiation, and some people have called these radiator fins. I call them infrared exhaust ports. So how well these radiator fins, these areas that get rid of a lot of the Earth's extra infrared radiation, how those things respond to these precipitation systems depends on the physics inside those precipitation systems, which we don't understand. We can make models do this. I mean, oftentimes it's pointed out, well, the global climate models do a pretty good job of showing us the average climate Yeah, that's what they've been tuned to do. They've got umpteen knobs, in terms of equations that you can tune, and we'll change this, and that looks pretty realistic. Okay. But it's very easy, apparently, to get the right answer for the wrong reasons. There's probably an infinite number of ways you could tune the models to get the average conditions right, but it's not the average we're interested in. What we're interested in is how is the atmosphere going to respond to the extra CO2. This is also from the instrument that I'm associated with. You hear about sea ice changing. Usually you think of sea ice as being this sort of static thing that just sits out there. And what this shows, these are daily images, shows that sea ice areas are actually very dynamic. They move around and react due to the movement of weather systems. These are around Antarctica, if you hadn't recognized the dark continent there. And you can see them move around basically because of low pressure areas moving around. I just wanted to, this isn't meant to do much of anything except just to show that the Earth is a dynamic system and everything is interconnected, and things you might think are static are actually pretty dynamic. Some recent global warming scares. I thought maybe some of this would come up. So I thought I'd mention it ahead of time. It's pretty well accepted that the recent hurricane activity in Florida wasn't due to global warming. It wasn't a particularly busy season. If you follow hurricanes, you know the Hurricane Center's been warning for years that Florida has gotten by easy for quite a few years, and that it was long overdue, although I think it was, 4 was a little excessive. I think the hurricane activity in 2004 was a little above normal. But what was really unusual is that Florida just happened to be in the way. These things move all over the place, and it just so happened they wanted to visit Florida last year. This idea was popularized with that movie, The Day After Tomorrow. As long as the Earth is round and as long as the tropics get more radiation than the poles, more sunlight, the ocean will find a way. It's a fluid like the atmosphere. It will find a way to move the heat out of the tropics to the polar regions. The Gulf Stream will not shut down. Now, I can't prove that, but that's my belief. And I think it's a minority view that could happen. But then I'm part of the minority on the global warming issue, so I don't want to be bad-mouthing minorities here. I just saw a recent study that suggested that the recent sea ice thinning in the Arctic is temporary and possibly part of a natural cycle, which is probably just more, this is possible. There's no proof. Tsunamis, for some reason, some people were claiming that tsunamis were related to global warming, that we've perturbed the climate system and we're going to have more tsunamis. Well, we can't even measure, or maybe we can now start to measure global warming. But when you've got things like El Nino that's moving gigatons of water sloshing all over the ocean, on time scales of a year, back and forth with huge climate fluctuations regionally, I would think that would have a much bigger effect on the tectonic plates than anything that we can do. Why do climate models predict so much warming? I believe that it basically comes down to that they're inherently unstable. The early climate models, it was difficult to get them to even model the average state of the climate system without drifting. And you find in a nonlinear system, nonlinear dynamical system like the atmosphere is, that you put some equations together to see how things react, and it's easy to, if you perturb the system, let's say in temperature, away, it wants to keep going away, unless you have the additional physics that come into play that keep it from getting too warm and push it back in the other direction. In fact, when we look at the average temperature of the tropical atmosphere on a daily basis, you see these fluctuations up and down. There can be huge excursions, but that there are natural processes that come into play. When the atmosphere goes too far out of bounds, it shoots off in the other direction, not to an equilibrium value. It'll overshoot and go cold, and then it'll overshoot again and go warm. The atmosphere is never in equilibrium, radiative or dynamical equilibrium, even though that's the basis of how we sort of understand climate change, is we're always talking about the radiative equilibrium of the Earth. You know, that we've perturbed the radiative equilibrium of the Earth by introducing CO2. Well, the Earth's never in radiative equilibrium. It's constantly changing. It's always out of equilibrium, and forces inside are going back and forth and fighting and whatever. Those are the things that I think we still don't understand very well. So another way of saying it is nonlinear processes interact in complex ways. It's getting now where climate models tend to not drift like they used to, but it's taken a lot of work to keep them from drifting. But are they only stable maybe for the way they've tuned the knobs? And you perturb the system with something that the model's not tuned for, like extra CO2, and it starts drifting again, maybe off to a new warmer state, maybe warmer than it should be. So I believe that models are still too simple to provide useful estimates of future warming. As you know, in areas like global warming, in the past, scientists have gotten a bad reputation because they tend to make predictions which invariably turn out wrong. I believe that this is one of those areas. But shouldn't we do something? Okay, well, I've already given you some opinions. Now we get into total opinions, okay? First of all, we have to recognize it's not possible to keep from polluting. I mean, if we can't agree on that, then we don't have any basis for discussion, unless you're of the very minority opinion that humans shouldn't exist on Earth, but then animals pollute too. But I guess that's okay because they're part of the natural environment and we're not. Now, given that we're going to have to pollute some, one of the issues that we have to decide then is how much pollution are we willing to live with? Typically, if you want to clean things up more and more and more, costs go up exponentially. So you kind of have to decide how much pollution are you willing to live with. And this is a very important point that is lost on a lot of people, but John Stossel has really been pushing on this in recent years when he finally came around to realizing that if we spend a whole lot of money on some environmental scare, that is money that's not available for other uses. So we have to be as informed as possible as we can be on all these issues to decide where we should put our money. This brings up the precautionary principle, which has gotten real popular in recent years. I read that its origins was in the environmental movement in Germany in the 1970s. It's usually encapsulated in this statement: when an activity raises threats of harm to the environment or human health, precautionary measures should be taken, even if some cause and effect relationships are not fully established scientifically. And I agree that if it looked like a doubling of CO2 had an 80% chance of causing our temperature to rise by 10 degrees, I'd be in favor of spending a lot more on reducing CO2 emissions than we are now. But the problem with the precautionary principle is that it really isn't applied honestly. It's only applied to one side of the equation. You know, you've got risks and benefits to everything we do. And the precautionary principle is an example of extreme risk adversity. And I think you realize that we live in an age where people are more and more adverse to any kind of risk, even though we live with it every day. You know, if you ride in a car, if you ride a bicycle, if you cross the street, You know, everything we do involves risk. A lot of people believe that applying this precautionary principle would greatly restrict innovation, making the world less safe. We sit and we complain about the threats posed by whatever the latest concern might be, and yet here we are, those of us that have children, we haven't had to deal with a third or a half of our children dying before their 5th birthday because we've built the wealth and knowledge base to invest in infrastructure. We've built the wealth. We've had inventions. We've discovered new drugs, whatever it is, things that we consider dangerous actually are safer than the alternatives 100 years ago. I mean, I have to fly a lot and it still scares me. You can tell me the statistics that it's 3 times safer to ride in a plane than it is to go in a car, but that doesn't help a whole lot. And I've also read that that back in the days of horses, when most people traveled by horse, that it was much more dangerous on a per capita basis. But it does look cool, you know. Electricity. I mean, that's some dangerous stuff, I can tell you. I do a lot of home remodeling, and I'm prone to not be turning the breakers off before I do the work. And I think electricity ought to be outlawed, personally, because it's... lasers, something that was invented in the early 60s, and they called it a technology looking for a use, because nobody could think of what we'd ever use them for. Pesticides, I'll leave pesticides here for just a minute. Precautionary principle tied to global warming. Oh, this is good. The longer I can go, the less I'll have to deal with hard questions, right? Okay, well, since global warming could potentially have negative consequences, shouldn't we restrict use of fossil fuels? Okay, well, that seems reasonable, except that affordable energy is what's necessary. It's sort of the lifeblood of economies, of the generation of wealth. And if you look historically, on average, in almost every country of the world, the human condition has improved in the last 100 years. There might be a couple of African countries that haven't improved at all. But overall, everything has improved, whether it's longevity, health, disease prevention, access to clean water. Not that it's where it needs to be yet, it isn't. Millions of people die each year because of unsafe drinking water. The wealthiest countries have the lowest population growth. I mean, if you want to stabilize the world's population, you need to get some of these countries that are undeveloped and get them to be wealthier. Now, of course, then you're requiring more energy. I'm not saying that I think one way or another is better. I'm saying that you got to look at all sides of the equation before you make decisions. Otherwise, you're not making decisions based on information, you're making them based on your worldview. Our energy future. I say petroleum will probably become increasingly expensive in coming decades. As time goes by, it seems like the supply of petroleum never actually decreases because they keep finding more, and they don't find much more than is needed. So actually, there may be a lot of petroleum that's out there for the coming centuries. But there's no question that we need new energy technologies, and they will come. And we haven't been sitting on our hands. The U.S., for instance, is investing $25 billion over the next 5 years. Maybe that's not enough, I don't know. But I want to point out that to get these new forms of energy, only the wealthy countries can afford to research them. And it's going to be the wealthy countries that develop these technologies. And if we do things to hurt our wealth now, then you might actually be shooting yourself in the foot. Obviously, they have to be relatively cost-effective. Solar isn't quite there yet. I mean, solar becomes popular when the government is providing subsidies for it. And I mean, I got a friend at work that built a passive solar house, and he's real pleased. So there's things you can do. Solar and wind, the energy intensity is pretty small, so it takes pretty large areas to get a significant amount of energy. Hydro, I think hydro actually produces like close to 8 or 9% of the world's energy. It's unpopular with some environmentalists because it changes the ecology of obviously of the river that it dams up. This would be great, is if someday, because there are such vast coal reserves on the earth, if we could find a way chemically where the coal is burned, let's say for electricity generation, to sequester the carbon dioxide and dump it back into the earth in storage. That would be great. One downside of coal, a little bit, is that it releases radioactivity when you burn it, but it's small. But then this is the risk of all life. I was just reading today how the dangers from natural pesticides are way above those from man-made pesticides. Half of the pesticides that there are in existence are natural because they're incorporated into plants. It's plants' natural mechanism to sustain life. Hydrogen fuel cells, that's one area that still has some technological challenges. Of course, you've got to have the energy to create the hydrogen. It's not like we've got lakes of hydrogen or caves that contain hydrogen that we can pump out. It's going to have to be separated from water or something, which takes energy. But if you could, for instance, if you could burn coal cleanly and generate the electricity, then we could be running on vehicles that are mostly, in essence, run on electricity through the hydrogen fuel cells. The main technology problem there, as I understand it, is because hydrogen per pound, well, let's not say per pound, in its natural state has way less energy content than gasoline. I forget what the factor is. It's some huge, it's 700, somebody here probably knows. It's a huge difference. And to have a tank of gas, the equivalent of a tank of gas, you've got to have hydrogen stored in tanks in your car to something like 6,000 psi, which is going to create a problem during wrecks, The space shuttle, chills it, which takes a lot of energy, puts it in liquid form, so it's very condensed, both the hydrogen and oxygen that the external tank uses for the space shuttle. Nuclear is really unpopular. A lot of energy experts say that you can't, in the next 10 or 20 years, you can't do much about the global warming issue unless you seriously reconsider nuclear. I'm just throwing these things out. Obviously, there's things that can be done to save energy that are available now, but this isn't an economic issue. This is sort of, what people want to do. You have to change the way people think if you're going to have them have a passive design, solar design built for their house. So there's different things that can be done in terms of efficiency. I'm running out of time and I need to leave you guys 5 minutes for questions. Right now, the main policy initiatives to reduce carbon dioxide production is the Kyoto Protocol, which just went into effect. I won't go into the details of all that, except that it'll have a pretty big economic impact on the countries participating. We aren't participating in it because the undeveloped countries like China and India aren't part of it, aren't required to be part of it, and they will soon outgrow us in terms of their CO2 emissions. There's a US equivalent sort of called Kyoto Light, which is sponsored by Senators John McCain and Joe Lieberman. I've already mentioned this. The downside of doing some of this stuff is they punish the use of energy. It's not like we're changing from chlorofluorocarbons to something else that doesn't hurt the ozone layer as much, that didn't cost that much. This is the basis of modern society. You got to have energy. And if you don't agree, you haven't been without electricity for 3 days in your house. If you do things to hurt the wealth of nations, it impacts the poor of the nations first. They're the first ones. The when gas goes to $2 to $3.50, you know, those of us that can afford it, it's not that big a deal. For those of the people that are living on the edge, it is a big deal. I personally believe, and this isn't a George Bush spiel here, what we really need is to promote freedom. I mean, because it's free people that allows the education, people to have education to make better decisions. Free markets is very efficient. The most destructive of environments are the countries that are very poor. There's countries in Africa that are totally deforested because that's their only source of energy. You know, they spend half their day foraging for trees or wood, downed wood. Revisit some environmental restrictions. I know everyone is against DDT, but it is an extremely safe way of preventing malaria. And there are millions of people that die every year in Africa because of the European Union's restrictions on them to not use DDT. So they don't dare use it, and millions of people die because of it. And I think that's a crime. So that's the end of my soapbox. Sorry, you've only got 3 minutes.
Thank you.